Welcome! In this video, we'll be tackling LeetCode problem number 953, verifying an alien dictionary. This is an interesting problem that challenges us to determine whether a list of words is sorted according to a custom letter order defined by an alien language. Let's dive in and explore the approaches to solve this problem step by step. In this problem, we are working with an alien language that uses the same lowercase English letters as we do, but the order of these letters could be different. The order is defined by a string called order, which is essentially the alien alphabet laid out in a specific sequence. Now, given a list of words written in this alien language, our task is to determine if these words are sorted lexicographically based on the given alien alphabet. For the input, we have two main components. First, words, which is a list containing up to 100 strings, each up to 20 characters long, with all letters being lowercase. Second, order, which is a string of exactly 26 unique characters representing the alien alphabet. For the output, we simply return true if the words are sorted correctly and false otherwise. Let's explore some examples to clarify how this works. Consider the first example. Here, the input consists of the words, hello, LeetCode, and the order string hlaptifgijknapkrstuvuxis. This order tells us how the alien alphabet is structured, where H comes before L comes before E, and so on. To check if the words are sorted, we compare them letter by letter. The first letters, H and L, are different. Since H comes before L in the alien alphabet, we can already confirm that hello comes before LeetCode. Thus, we return true. This demonstrates how the first differing letter determines the sorting order between two words. Now, let's look at another example. Here, the words are word, world, row, and the alien alphabet is defined by order equals world absefgijknapkrstuvuxis. When comparing word and world, the first differing letters are O and R. According to the alien alphabet, O comes after R, which means word does not come before world. Hence, the words are not sorted correctly, and we return false. This highlights how the alien dictionary's order directly determines whether the list of words is sorted or not. Finally, consider the case where the input includes apple, app, and the order is the standard English alphabet, A B C D F G H I J K L M N O P Q R S T U V W X Y Z. Here, the shorter word app is a prefix of the longer word apple. Lexicographically, a shorter word should always come before a longer word if their shared prefix is identical. However, in this case, apple appears before app, which violates the sorting rule. Therefore, we return false. The constraints of the problem ensure that all characters in order are unique, and the edge cases to consider include single word lists, identical words, and prefix relationships. These details should guide us as we verify the sorting of the given words. To solve the problem of verifying whether a list of words is sorted according to an alien dictionary order, we considered a few approaches. The first is the brute force approach. Here, the idea is to directly compare each pair of adjacent words. For every character in these words, we determine their positions in the given alien alphabet and check for violations of the order. If any pair is not in the correct order, we return false. While this method works, it is inefficient due to the repeated searches for character positions within the order string. This makes it computationally expensive for large inputs. On the other hand, the optimized approach improves on this. The key insight is to pre-process the alien order string into a mapping of characters to their indices. With this map, we can compare words by their positions directly, significantly reducing redundant computations. If two adjacent words have a mismatch, we only need to check the first differing characters. Additionally, we ensure shorter words appear before longer ones when one is a prefix of the other. This streamlined comparison process offers a much better balance of efficiency and simplicity. The optimized approach has clear advantages in terms of time and space complexity. Constructing the character mapping takes constant time since there are only 26 letters in the alien alphabet. Word comparisons are done in linear time relative to the length of the words, making the overall complexity O, n*m, where n is the number of words and m is their average length. The space complexity is minimal as we only store the character mapping, which is fixed at 26 entries. This makes the approach both scalable and memory efficient. Another alternative we considered is the transformation approach. Here, each word is converted into a list of indices based on the alien order. These transformed words are then checked to see if they are sorted. While this method simplifies the comparison logic and leverages Python's built-in sorting functions, it requires additional memory to store the transformed words. This results in a higher space complexity of O and *m, making it less desirable for scenarios where memory usage is a concern. After evaluating all the options, the optimized approach using a hash map for character comparison stands out as the best choice. By pre-processing the alien order string into a mapping, we eliminate redundant computations and achieve the most efficient solution. The transformation approach, while simpler to implement, is less memory efficient due to the storage of transformed words. The brute force method, though straightforward, is too slow for handling large inputs effectively. The key insights that make the hash map approach optimal include the ability to pre-process the alien order for constant time lookups, directly comparing words without additional memory overhead, and handling mismatched characters or prefix relationships seamlessly. While pre-processing the hash map adds a small setup cost, this is negligible compared to the overall efficiency gain it provides. For these reasons, the hash map approach is the most scalable and balanced strategy for solving this problem. To solve the problem of verifying if words are sorted according to an alien dictionary, we start by understanding the custom order provided. The alien dictionary gives us a unique sequence for the alphabet, and our goal is to ensure the list of words follows this sequence. The first step is to create a mapping of each character in the alien alphabet to its index in the order. This mapping allows us to determine the relative position of any two characters instantly, which is crucial for efficient comparison. We can use a dictionary, or hash map, where the keys are the characters and the values are their positions in the alien order. For example, if the order is flapdifgijknaprstuvuksis, the mapping is H0, L1, A2, Z25. Once we have this mapping, we proceed to compare adjacent words. By iterating through the list, we compare each word with the next one. For each pair, we look at their letters one by one. The first letter that differs between the two words determines their order. Using the alien mapping, we check if the letters are in the correct order. If not, we can immediately return false. Additionally, if one word is a prefix of the other, the shorter word must come first. For example, app should come before apple. By following these steps, we can systematically verify the order of the words. Now, we address specific scenarios to ensure our solution handles all cases correctly. For an empty list of words, we return true, since there's nothing to compare, and the list is trivially sorted. Similarly, if there is only one word, we return true because no comparisons are needed. Another important situation arises when words share identical prefixes. For example, if we have app and apple, the shorter word, app, must come first. If this condition isn't met, the order is invalid. After handling all word pairs and ensuring they satisfy the alien order, we can confidently return true. This indicates that the list of words is sorted according to the alien dictionary. Some key insights make this algorithm efficient. First, by mapping characters to indices, we convert the problem into numeric comparisons, allowing constant time lookups for each character. Second, we optimize by exiting early if we find any pair of words out of order, saving unnecessary checks. Lastly, prefix handling ensures correctness when one word is a substring of another, which is a common edge case in string comparisons. The algorithm relies on simple yet effective data structures to achieve its goals. The main structure is a dictionary, or hash map, used to store the character-to-index mapping for the alien alphabet. This allows O1 lookups when comparing characters during the word checks. Beyond this, no additional data structures are needed, as we process the input list of words sequentially. Now, let's analyze the time and space complexity of the solution. The time complexity is O(C), where C is the total number of characters across all the words. This is because we iterate through each character exactly once during the comparisons. The space complexity is O(1), excluding the input storage, since the only extra space we use is for the alien order mapping. This mapping has a fixed size of 26 entries, as it corresponds to the lowercase English alphabet. These efficient use of resources ensures the algorithm performs well even for larger inputs. Let's walk through an example to see the algorithm in action. Suppose the input words are, hello, LeetCode, and the alien order is flapdifgijknapristuvuksis. First, we build the mapping H0, L1, A2, Z25. Next, we compare the first pair of words, hello and LeetCode. Comparing letter by letter, H is checked against L. According to the mapping, H comes before L, so this pair is in the correct order. Since there are no more words to compare, we return true, indicating the list is sorted. Now consider an edge case, where the words are apple, app. We compare apple and app. The first three letters, A, P, and P, are identical, so we move to the next condition. Here, we see that app is a prefix of apple, which means the shorter word should come first. Since this isn't the case, the order is invalid, and we return false. These examples demonstrate how the algorithm effectively handles both standard and edge cases, ensuring correct results in all scenarios. This solution verifies if a list of words is sorted according to a given alien dictionary. Let's break down the code. 1. Mapping alien dictionary order. The first step creates a mapping, order_index, of each character in the alien alphabet to its respective index. This allows for quick comparisons of characters based on their custom order. 2. Iterating through words. The algorithm iterates through adjacent word pairs in the words list. The goal is to ensure that each word is lexicographically less than or equal to the next word according to the alien dictionary. 3. Character by character comparison. For each pair of words, word 1 and word 2, we compare their characters one by one. If we find differing characters, we compare their indices from order_index to determine their order. If word 1's character is greater, the list is not sorted, so we return false. If characters are in the correct order, we break the loop and proceed to the next pair. For handling prefix cases, if one word is a prefix of the other, e.g., apple and app, the shorter word should come first. This is checked by comparing the lengths of word 1 and word 2 after their common prefix has been processed. If word 1 is longer, the list is not sorted, so we return false. 5. Returning true. If all word pairs satisfy the sorting conditions, the function returns true, indicating the list is correctly sorted. The time complexity of this solution is n*m, where n is the number of words and m is the average length of the words. This ensures efficiency even for large inputs. The space complexity is O1, aside from the space used for the order_index mapping. Here, we begin by importing the necessary utilities and defining our solution class. The main method, isAlienSorted, takes two inputs, an array of words and a string representing the alien dictionary order. The first step is to map each character in the alien dictionary to its corresponding index. This is done using a hash map, where the key is the character, and the value is its position in the order string. Next, we iterate over pairs of adjacent words in the array. For each pair, we extract the two words, word 1 and word 2, that we need to compare. We then initialize a flag, rWordSorted, which will help us determine if the two words are in the correct order. To compare the words, we iterate through their characters up to the length of the shorter word, comparing character by character. If we encounter two different characters, we use the order index map to check their relative positions in the alien dictionary. If the character from word 1 comes after the corresponding character in word 2, it means the words are not sorted, and we return false. Otherwise, we set the rWordSorted flag to true, as the words are in the correct order up to this point. If we determine that the characters are sorted, we break out of the character comparison loop and move on to the next pair of words. However, if all characters in the shorter word match, we need to ensure that word 1 is not longer than word 2. This is because a longer prefix would make the words unsorted. If word 1 is longer, we return false. If none of these conditions are violated throughout the comparisons, we conclude that all the words are correctly sorted according to the alien dictionary order and return true. This method ensures an efficient and systematic validation of the word order, leveraging the mapping of characters to their indices and iterating through the words and their characters as needed. To solve this problem, we need to verify if the words are sorted according to the given alien dictionary order. In example 1, the input words are hello and LeetCode, and the alien dictionary order is specified as flapdifgijknapristuvuksis. First, we map each character in the given order to its respective index. This creates a dictionary called order_index, where each character is associated with its position in the alien order. For instance, H is at index 0, L is at index 1, and so on. This mapping allows us to quickly compare the relative order of any two characters. Next, we iterate through adjacent word pairs in the words list. The first and only pair is hello and LeetCode. To determine if they are sorted, we compare their characters one by one. Starting with the first characters, H and L, we find that in the alien order, H comes before L since their indices in order_index are 0 and 1, respectively. This confirms that the pair is correctly sorted. Now that we've confirmed the first pair is sorted, we check if there are any more pairs to compare. In this example, there are no additional pairs, so we conclude that all words are sorted according to the alien dictionary. As a result, we return true. Moving to the second example, the input words are word, world, and row, with the alien dictionary order specified as world_absefgijkstuksies. First, we create the order_index mapping, assigning each character in the alien order its index. For instance, W corresponds to 0, O to 1, R to 2, and so on. This mapping helps us efficiently compare characters based on their relative positions in the alien dictionary. We then begin comparing adjacent word pairs, starting with word and world. Comparing their characters one by one, we observe that W matches W, O matches O, and R matches R. Moving to the next characters, we compare D and L. Referring to order_index, D has an index of 3, while L has an index of 7. Since 3 is less than 7, this pair is correctly sorted. Next, we compare the second pair, world and row. Comparing their first characters, W and R, we find that W has an index of 0, while R has an index of 2. Since 0 is greater than 2, this pair is not sorted. Therefore, the words are not in the correct order, and we return false. In the final example, we handle a prefix case where the input words are apple and app, and the alien dictionary order is the standard alphabetical order. As before, we create the order_index mapping, where each character maps to its position in the alphabet. Comparing the only pair, apple and app, we start with their first characters, A and A, which are the same. Moving on, we compare P and P, which also match, and then another P and P, which still match. At this point, we have exhausted all characters in app. However, apple still has remaining characters, and its length is greater than app. According to the alien dictionary rules, a longer word cannot precede its prefix, so this pair is not sorted. As a result, we return false. To analyze the time complexity of our solution, let's break it into distinct steps. First, we need to create a mapping of each character in the alien order to its index, using the order_index dictionary. Since the order string typically represents an alphabet with 26 characters, this step is constant time, O1. Next, we iterate through the list of words to compare each pair of adjacent words. If there are n words, we perform n1 comparisons, resulting in O(n) for this step. Lastly, for each pair of words, we compare their characters one by one up to the length of the shorter word. If m represents the average word length, this character-by-character comparison takes O(m) per pair. Since we compare n1 pairs, the total time complexity for this step becomes O(n*m). Combining all these steps, the dominant term is O(n*m), which reflects the overall time complexity of the solution. The overall time complexity of the solution is O(n*m), where n is the number of words and m is the average length of the words. This accounts for comparing all pairs of words and their characters. Now, for the space complexity, we begin with the order_index dictionary, which maps each character in the order string to its index. Since the size of the order string is fixed at 26 characters, the space required for this dictionary is O1. Additionally, temporary variables used for iteration, such as word1, word2, and indices like I and j, require constant space, which also contributes O1. Lastly, the input words and order are read-only and do not require extra space beyond their given sizes. Combining all these factors, the overall space complexity is O1, as the solution uses constant auxiliary space regardless of the input size. When we evaluate the best, average, and worst cases, the time complexity varies slightly based on the input. In the best case, the words are already sorted, and the first character mismatch occurs early in each pair. This allows us to terminate comparisons quickly, making the complexity O(n). In the average case, we assume that all words need to be compared up to their average lengths, resulting in O(n*(m). The worst case occurs when all pairs of words are identical up to the length of the shorter word, requiring maximum comparisons, which is also O(n*(m). Comparing this to a brute force approach, where every character of all word pairs is compared without early termination, we see the naive solution also has a complexity of O(n*(m), but is less efficient in practice. The current solution optimizes performance by leveraging the order_index dictionary for O(1) character comparisons and breaking early when mismatches are found, making it more efficient for sorted or partially sorted inputs. To further justify the time complexity mathematically, the outer loop iterates n1 times, as it compares pairs of words. For each pair, the inner loop iterates up to m times, where m is the length of the shorter word. This results in approximately n1*(m) comparisons, which simplifies to O(n*(m). On the space complexity side, the algorithm uses constant-sized structures, such as the dictionary for character indices and a few temporary variables for iteration, resulting in O(1) auxiliary space. In conclusion, the algorithm is highly efficient with O(n*(m) time complexity and O(1) space complexity, making it an optimal solution for verifying the order of alien dictionaries, even with large inputs. When solving this problem, there are a few common mistakes to watch out for. One major issue is misinterpreting the alien order mapping. If you compare characters using their default lexicographical order, such as with Python's ord function, you'll get incorrect results because the problem defines a custom order. To fix this, you need to create a mapping that assigns each alien character to its position in the given order. Another frequent mistake is not handling prefix issues correctly. For instance, if apple appears before app in the list, it violates the rules since the shorter word must come first when a word is a prefix of another. To avoid this, ensure your logic explicitly checks for such prefix relationships during comparisons. Other common pitfalls include inefficient pairwise comparisons. Some solutions attempt to compare all words in the list against each other, which drastically increases time complexity to O(n²*(m). Instead, you only need to compare consecutive pairs of words, which is much more efficient. Another mistake is overcomplicating the character comparison process. Overly complex code can introduce logical errors and make your solution harder to understand. A better approach is to use helper functions or concise one-liners for clarity. Finally, many solutions fail to consider edge cases, such as empty lists, single-word inputs, or very long words. These scenarios can expose hidden bugs, so it's crucial to test your solution against diverse inputs to ensure robustness. This problem is not just about verifying an alien dictionary, it tests your ability to handle custom orderings and implement comparisons efficiently. A key insight is to focus on creating a clear mapping of the alien order and addressing edge cases like prefixes explicitly. This pattern of custom mappings or orders is common in problems like sorting based on rules or validating sequences. Recognizing such patterns can help you tackle similar challenges more easily. Additionally, efficiency matters here, especially during interviews. Avoid unnecessary computations, like comparing non-consecutive word pairs, and prioritize clarity and optimization. Be prepared to explain edge cases as well. Interviewers value attention to detail and robust solutions. Related problems, like LeetCode 242 for anagrams or the harder LeetCode 269, which requires deriving the alien order, can also help you build these skills. There are a few alternative approaches you could consider for this problem. The first is iterative character comparison, where you directly compare the characters of consecutive words using the alien order mapping and stop at the first mismatch. This method is simple and efficient, with a time complexity of O(n*(m), but it requires careful handling of prefix relationships. Another option is sort-based validation, where you sort the words according to the alien order and then compare the sorted list to the original input. While easier to implement, this method is less efficient due to the O(n*(m)log(n) complexity of sorting. Lastly, there's tree-based validation, which involves building a tree from the words and validating the order based on the structure. This approach can be useful for more complex extensions of the problem, like prefix queries, but it is generally overkill for the basic validation task. Great job following along. To summarize, this problem required us to verify sorting based on custom rules using a hash map. It's a great example of how to handle non-standard sorting with efficient comparisons. Remember, practicing problems like these builds strong problem-solving skills. Thanks for watching, and see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!